Today we learn about relation. Now, what is the relation? So, a relation R from a non-empty set A from a non from a non-empty set A to a non-empty set B is a subset of their Cartesian product. Is a subset of their Cartesian product. Their Cartesian product A cross B. Right. Now we get what is relation. Now a relation R is from a non-empty set A to a non-empty set B is a subset of their Cartesian product. Now we get relation. Now what is domain and range of a relation? Domain and range of a relation. Domain and range of a relation. So what now the set of all first elements of the ordered pair pairs in a relation R from a set A to a set B is called domain of R. So the first element, set of all the first elements of the ordered pairs in a relation R from A to B is called domain of R, and the set of all the second elements of the ordered pair in a relation R from A to B is called the range of R. So the set of all second elements of the ordered pairs in a relation are from A to B is called range of R. Okay, so we get what is a relation, and what is domain and range of a relation. Now let us see one more thing. Suppose we have two sets, let us say A and B, and let cardinality of A is 3, or okay, not 3, let's say cardinality of A is P and cardinality of B is Q. Then the total number of relations from A to B is equals to 2 to the power PQ. That's we need to know. Okay, now let's go to the types of relations. For relations, we have different types. Let us start it with, let us take a set A. Okay, before everything, let us take a set A. A be a set. Okay, now clearly we know that phi is a subset of A cross A. We can say that. So it is a relation on A. Then it is called, this relation is called void relation or empty relation. Okay, this is easy. Now number 2, clearly A cross A is also a subset of A cross A, right? So it is also a relation on A. Now then it is called the universal relation. Okay, now here come the important ones. Identity relation. Identity relation. So what do we mean by that? We have the set A. Okay, so what is the relation? Let the identity relation be defined as IA. This is nothing but this is called an identity relation. So if we explain it, how we can explain that every element of A is related to itself only. That is, every element of A is related to itself only. Right. Now we take reflexive relation. We will understand more about this by an example. I will do an example also. Now, what is the reflexive relation? Now, a relation R on the set, we have taken the set A, so on a set A is said to be reflexive if and only if A comma A belongs to R for all A belongs to A. Right? So when we call a relation R is a reflexive relation, that is for all A belongs to A comma A will be in R. Right? So this is reflexive relation. Now how can we distinguish identity relation and reflexive relation? We can easily verify that. How? By an example we can see it. Let us take an example. Like let A be 1, 2, 3 and R be 1, 1, 1, 2, 2, 2, 3, 3. Clearly this is reflexive. Why? Because we have 1, 1 for every A. For every element of A, 1, 2, 3, we have 1, 1, we have 2, 2, we have 2, 3. But here we have 1, 2 belongs to R. So it is reflexive clearly, but it is not identity. Because what now, in identity relation we have every element should be related to itself only. That's why 1 2 belongs to R means it is reflexive but not identity. Okay, so we get what is the difference between identity and reflexive. Okay, now we see two more things. What is a symmetric relation? This is also very easy. Now a relation, let's say R, a relation R on a set A is said to be symmetric if and only if AB belongs to R implies BA belongs to R for all AB belongs to A. Sorry, not this. I have write in ordered paired. Okay. Now one more. I will give us example of symmetric relation also. So don't worry about it. So let us say transitive relation. Transitive relation. Now similarly we can write. Now what is the transitive relation? Now let A be a set and R be a relation on A. A relation on A. Now R is said to be transitive if and only if AB belongs to R, BC belongs to R, implies AC also belongs to R for all A, B, C belongs to A. Okay, so we get it now. AB belongs to R and BC belongs to R. That implies AC will also be in the relation. And a relation, let us say a relation R on a set A is called equivalence relation. Equivalence relation if it is reflexive, symmetric and transitive. Okay, so this is the definition part. Now to explain all of this, let us do a question. By a question we can understand what I am trying to say. Okay, so let's do a question. This is a very good question. This question have arrived in JEE means 2025. Okay, So we have said that A is 1, 2, 3, 4, and R we have 1, 2, 2, 3, 3, 3. In the relation R we have these three elements. Now what they are asking, that they are asking then the minimum number of elements needed to be added in R so that R becomes an equivalence relation. So what we have just studied earlier, then an equivalence relation is reflexive, symmetric and transitive. Okay, so let's go one by one. Let us check the reflexibility. Let's say if R is reflexive, then for every element in A we need to have the ordered pair A belongs to R. So for reflexivity, how many elements we need? Then 1, 1, 2, 2, 3, 3, 4, 4 needs to be in R. Now we already have 3, 3 in R, so we don't need to count that. So for reflexibility we need to add these three elements. Okay, for reflexibility we need to add this three elements. Now for symmetricity, now if R is symmetric, then what do we need to do? Suppose R is symmetric, then from here we get three elements, right? If it is symmetric, then we have 1, 2 in R. Then that implies 2, 1 also should have to be in R because it is symmetric. No, so 1, 2 in R, that implies 2, 1 also be in R. Similarly, 2, 3 is in R, that implies 3, 2 also need to be in R, otherwise it will fail the symmetricity. No. Okay, so we get 1, 2 in R, then 2, 1 is R, and 2, 3 is already in R, so we need to have 3, 2 in R. From here we get 2 elements. Now if R is transitive, if R is transitive, then we have 1, 2 in R, we have 2, 3 in R. Now since we have taking that R is transitive, that will implies 1, 3 in R. So you get one more element. Now see this is where the error occurs. We are taking this, everything is fine. For reflexivity we get 2 elements, for symmetricity we get for reflexivity we have 3 elements, for symmetricity we get 2 elements, and for transitivity we have 1 element. So how is R looking right now? We have 1, 1, we have 1, 2, we have 2, 2, we have 2, 3, we have 2, 1, we have 3, 3, we have 1, 3, and we have 3, 2, right? So how many elements? 1, 2, 3, 4, 5, 6, 7, 8, right? But see, if R is an equivalence relation here, then it has to be reflexive, symmetric and transitive. But when we check the transitivity, we get 1, 3 from here. If we add 1, 3 here, then it is not symmetric, because if it is symmetric, then we need to add it the 3, 1. So exactly, since we are adding this, so we need to add 3, 1 also. Then it is an equivalence relation. There is no other possibility. So we have some elements. We have 1, 2 here, we have 2, 3 here, and we have 3, 3. initially they have given. So what are the elements we are adding on? We are adding 1 1, we are adding 2 2, we are adding 2 1, we already had 3. So oh, here I have missed one. We need to have here 4 4 as well. So we had 3 3, so we had 1 3, we had 3 2, 3 1 and 4 4. So 1 2 3 4 5 6 7. So 7 is the correct option. So OPT option B is the correct answer. Okay, got it. So we need to add 7 more elements for R to be an equivalence relation. Okay, let us do one more question. This is also arrived in JEE 2025 mains. Okay, what they are saying now, they are saying they are defining a relation R on the domain on the interval 0 comma pi by 2 open interval by x related to y if and only if sec square x minus tan square y equals to 1. Now we need to check R whether it is reflexive or symmetric or transitive or equivalence. We need to check that. So what do we need to do? Let us do it. Now let us check step by step. Let us check for reflexibility. When we say a relation is reflexive, that for all x belongs to the set, x comma x need to be in the relation. So for reflexivity, what do we need to do? To check the reflexibility, so what? We can check whether x are x if and only if sec square x minus tan square x equals to 1. This is obvious because this is the identity. In this domain 0 comma pi by 2, we know this is an identity. So clearly R is reflexive. R is reflexive. So we have no issue because we know the identity. So clearly this is reflexive. There is no doubt about that. Now for symmetricity. Now let x comma y belongs to R, or we can say that x or y. What does it mean? That this implies sec square x minus tan square y equals to 1. If we consider that x comma y belongs to R, then this will occur, sec square x minus tan square y equals to 1. Now if it is symmetric, then what do we need to say? Show that y comma x also be in R. That means what do we need to show? If y comma x is in R, then we need to show that sec square y minus tan square x is equals to 1. This is we need to show. Our purpose is that we need to show this. Okay, now let's do this. So let us take this left hand side to be sec square y minus tan square x. Okay, now we know what do we mean by sec square y. We can write sec square y like this, 1 plus tan square y minus. Now what is tan square x mean? That is nothing but sec square x minus 1. Right, so there is what? If we do like this. What? 2 minus sec square x minus tan square y. Just the simple calculations, right? Now we already have sec square x minus tan square y equals to 1. So 2 minus 1, that is equals to 1, that is RHS. So from here we get that implies yx belongs to R. So R is symmetric as well. Now we have to check the transitivity. Now for transitivity, what we can take like this. Let us say x comma y in R and y comma z in R. If they both these ordered pairs are in R, that means what? Then by the question one can we say now sec square x minus tan square y is equals to 1 and sec square y minus tan square z is also 1 by the given hypothesis. So what do we need to show? We need to show that x comma z is in R. That means what? Now sec square x minus tan square z is equals to 1. We need to show this, right? So how can we show it? Clearly we have these two equations, right? Maybe let this be 1 and this be 2. Just add 1 plus 2. Then what? Sec square x minus tan square y plus sec square y minus tan square z is equals to 1 plus 1 2. That implies what? Sec square x minus tan square z plus sec square y minus tan square y. This is equals to 2. Now this is equals to 1. No, sec square y minus tan square y is equals to 1. This is a common identity. So if we put that in the right side, then sec square x minus tan square z is equals to 2 minus 1. This is equals to 1. So we can, from here we can say that x comma z is in R. So R is transitive as well. So R is reflexive, symmetric and transitive. That implies that R is a equivalence relation. Now let us check the option. So option 2 is right. This is an equivalence relation.